All right, welcome everyone to the last talk of this morning. I will speak about something that is maybe a little bit off the main trail that you hear in image analysis at the moment, which is deep learning. As Tan Moi, I also think sometimes it's interesting to imagine what happens if you don't have training data and what can you do. So I am Andreas Fischer. I'm in Fribourg, Switzerland, doing research. This is my local orientation. Internationally, I feel part of the global community on document analysis and recognition. It's a very fine community that will meet next year in Switzerland. So I would like to invite you all to join in Lausanne next year and hear more about all of that. Today, I talk about advances in graph-based keyword spotting for supporting quantitative paleography. Now, a research community, I imagine like a hike in the mountains, and there is always a trail. And this trail at the moment, this is the deep learning trail, so I dare take you a little bit off the road into the forest to show you something, and I hope you will find it worthwhile, both in performance and utility, and then at the very end also come back to the trail, not to get lost, of course, for arriving at the restaurant on top of the mountain. Keyword spotting is a topic that sometimes has to deal with very little annotated training data. This is why we need to think a bit differently sometimes. Imagine in a completely unrelated scenario that the US has a constitutional crisis and wants to consider again the writings of George Washington. So to see where it all came from. And then the scholar goes to the Library of Congress and finds hundreds and thousands of images ready-made that contain the letters. And of course, this is very, very cumbersome to browse. And keyword spotting is a nice tool that would allow you to select an instance of what you're interested in. For example, here the word orders, and then get some results from the complete huge collection that are somehow similar to orders, ideally the same word. And in the so-called query by example scenario, indeed, we have no annotations whatsoever. Imagine that you open one of the letters as an image and you draw a kind of a rectangular box around the word, and this is all you need to kick off the system. So it does not need annotations or machine learning per se. And it can also be applied to non-textual elements. Maybe you're looking for the signature of George Washington, maybe you're looking for certain stamps, and you can basically use the same techniques for that. Now, the first question that we all have to answer if we work with the computer is how do we present the handwriting to the computer? And this step is crucial because here we decide what kind of information the machine actually has available. The raw information is, in more mathematical terms, a matrix. It's pixels. It's already quantified in some discrete numbers. Every pixel has usually 3 numbers for red, green, and blue. But if you don't do learning using the matrix directly for comparing, it's really not a good idea. Because if the handwriting moves just a little bit, all the matrix becomes completely different. So usually some form of abstraction is needed, and it was discussed a lot in this conference. How can we define pertinent features for handwriting? On the first day, I remember the hinge feature was put forward as a very good way of looking at curvature, and there are many more. And you can also ask a neural network to learn this representation. In the end, you will say, my handwriting is n real valued numbers. And this is what you give to the machine. Another technique that is common is to read handwriting from left, or in reading direction, here from left to right, with an analysis window. And basically, you don't describe the whole image, you describe what is visible in the window, and you create the sequence, sequential information. So that's the first part, that's the middle part, that's the end part, and this is what you provide to the machine. To the very right is the thing I want to talk about, which is a structural representation of the handwriting by means of a graph. It's maybe related to what we've heard from Archetype, what is a grapheme. You were talking about parts that constitute the handwriting and how they are related. And that's exactly the idea of a graph. You see here nodes. They are the parts chosen as points on the stroke. And you see edges that connect them. And the meaning of an edge in this scenario is they are neighboring on a stroke. But you can define the parts also differently and the relations also differently. All of that is called a graph. And if you go that way, this is basically where you have a bifurcation in the research community. You go from the so-called statistical pattern recognition to the structural pattern recognition. It's a little bit another way, but it's also paved, actually. So since many decades, people have been working on that as well. On the left-hand side, you have these n real-valued numbers, and it's very nice mathematically. You can add vectors, you can calculate the mean, and so on. And there is many algorithms available to treat this kind of representation. However, it's a bit fixed. You have to decide beforehand what are the n numbers that are interesting. And once you have decided that, every sample will be judged in the same way. On the right-hand side, you have more flexibility. A complex handwriting will have more nodes and more edges, and you can model all the intrinsic, maybe also the ligatures in detail by using a definition, so it's variable in size, and it can capture things you like. You can encode them as additional information on the nodes and on the edges. You can add feature vectors wherever you like. Which is why a graph indeed is a more general representation than a single feature vector. However, it comes at a cost. So when you want to work with graphs, compare them, it's usually quite complex. And this is not a matter of how much CPU and RAM do you have. It's a matter of complexity. And often there are problems involved that are simply not solvable even by the best machine we have. You run into these problems, and accordingly, there is also fewer algorithms that are available. So you cannot just plug it into a deep neural network. It will not work per se. So I will still, at some point, colleagues and myself, especially the PhD student Michael Stauffer and my colleague Kaspar Riesen, we sat together and thought, let's try it on the right-hand side for keyword spotting. What is possible? What are maybe also the limitations? And this result of this investigation I will present a bit systematically. This is the system that we have designed. We start with the document, and in a first step, we do some image processing. We rely on binarization because we want to go towards an abstraction. So we want to know what is ink and what is the background of the paper or parchment in other data sets. And so we end up with a binarized black-white representation where the ink is black. And we also assume that we have words. Of course, there's errors if we do the segmentation, but this is where we start. And from these images, we extract our graphs. And you can see some samples already here. Afterwards, I have said you can select one query image, like orders. So you select that, you put it into the system, and then this sample is compared to all the graphs that you have in the database. And ideally, on the right-hand side, the most similar graphs will pop up and guide you towards new documents that you want to read with respect to your query. And we hope that, like in a Google search, the top hits are really the relevant ones. The first step is basically deskew the whole document, that it's more or less straight. Afterwards, we apply a binarization. We don't use a very complicated method here. It's a difference of Gaussian that then locally enhances the edges a little bit, and then we threshold. It gives very good results closely around the writing. It cannot get rid of artifacts like stains and folds and things like that. But we have a very good localization of the word on the page. So for us, it's important in the surrounding of the word, it should be as clean as possible. This gives us the words, and then we go a step further. We want to abstract also from the thickness, so we don't want to take that into account, the thickness of the stroke. We are interested in what is somehow the ideal stroke. the shape, inner shape of this character, and we end up with this skeletonized words. Afterwards, we extract graphs from them, and here maybe I have to be a tiny little bit formal. So what is a graph? Mathematically, it's a set of nodes that are linked together with edges. Think, for example, about the molecule. The nodes are the atoms, and the way they are linked together, these are the edges. And indeed, this is in computer science one of the most general data structures that you can think of, and there is almost nothing that you cannot represent with a graph. And indeed, it's used to represent text, web pages, fingerprints, neural networks, or graphs. And also handwriting, which is what we want to do. In our case, we have found one representation which might seem rather simple, but that just experimentally worked best over a couple of years of experimentation. We so far didn't find a significantly better way of doing it, unfortunately. We hope we do someday. In the skeleton, we tag the endpoints and the intersections. And then we also add, at regular interval, nodes along the skeleton, instead of trying to put in splines, for example, as Vinod has been talking about, which would be a more abstract representation. We just put a couple of more nodes in between. And we call that key point graphs, that somehow should capture the essence of the shape, and especially this is one representation, so it captures the global structure of the handwriting. Here is some visualization of the data sets that we have been working with. In effect, some famous letters of George Washington. It's a rather small data set of 20 pages, mid-18th century, written during the war. George Washington himself and some of his aides. The Parzival database, this is from the 13th century, Middle High German, epic poem. Then we have the Konzilsprotokolle. This is the meeting minutes from a German university, also end of 18th century. And finally, the botany data set, which is some descriptions of the botany in British India in the beginning of the 19th century. So you can see that the graphs that come out, they look a little less fluid to the human eye than what we have in the original image, but from this distance, I hope it's somewhat convincing that they capture the general shape. We have chosen several data sets to make sure that we don't get stuck in a local optimum just on one of them. And they are in botany, for example, has a lot of variation within the data set. Parzival as well. George Washington is relatively clean because it comes from a single hand. And actually, no two, but the aide also tried to write exactly like George Washington. So visually, it's really convincingly one writing style. Okay, so what's going to happen to our graphs? Now we come to somewhat the central part of the whole system, the machinery, the motor. And this is, given two graphs, are they similar or not? This is the question we have to answer if we want to spot similar samples. And there is a very large number of methods that have been proposed, including, maybe you've heard about spectral methods or graph kernels. So in our research group in Bern, which was led at the time by Horst Bunke, we are naturally inclined to go for the graph edit distance, which is considered as somewhat the canonical way of comparing graphs, a standard way. It has the nice property that it can be applied to any type of graph. So I can have these arrows indicate on the leftmost graph that it's a directed one. The edge direction matters. There can be labels on the nodes, for example, in form of colors or in form of feature vectors to describe the image properties around the node. And there is also the possibility to label the edges. This is maybe if you have tried to find the shortest path in a graph. This is, for example, the distance between the nodes as one number, but it can be anything. And this is the nice property of the graph edit distance. It can cope with that variety. I allow myself again to really go into a little bit of detail to show you what the graph edit distance is. The basic concept is that you have one graph to the left and one to the right, and you ask yourself, how can I modify the graph step by step so that the left graph eventually becomes the right one? What can I do? I can remove nodes, I can add nodes, I can change the labels, I can also remove and add edges. And eventually I'm interested in the best way to do that. So the least effort from left to the right. Here, for example, I could say remove a node and 3 edges in one step. Then what happens? 2 edges are removed. Then it's a little bit difficult to see, but the color changes on one of the nodes. And finally, I have arrived at the right-hand side. But there is many ways to do that. So this is another way of transforming the graph. This is another way of transforming the graph. And I'm looking for the best way. So first, I have to attribute some cost to these operations. Let's say the cost is 1 for deletion and insertion and substitution. And then I can judge each of these paths according to their cost, and I try to find the cheapest one. And this is basically the definition of the graph edit distance between graphs. I can take the labels into account when I do a substitution. For example, if 2 nodes are close together, it should cost less than if 2 nodes are really far apart. And there is some human engineering involved in that to come up with a really good cost function. All right, there is one big problem with the graph edit distance. It's not usable in practice. It's a bit unfortunate. So if you want to have an exact solution, you have to check this node could go here, 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 here in the other graph. Once you made that decision, the second node also can go anywhere and can go anywhere. And if this blows up exponentially the number of possibilities that you have to explore, and even if you have 2 graphs with only 10 nodes, you already have to compute 40 million of these edit paths to find the best one. So it's not practical, but we have been working, many people have been working on good alternative solutions, and in the past years we have more or less for handwriting, they converge towards this one. It's an approximation, so it calculates not the real distance, but something similar. And this concrete approximation is always a bit too small. We know it. If we calculate it, it's a bit too small, but especially if the graphs are similar, there is a very close match to the real graph edit distance. And the advantage is that it can be computed even for graphs that have 10,000 nodes, for example. That's much more than 10. Okay, so this gives us the tool. And we can apply it and basically finalize our system. And when we put all of that together, what we end up with is this hit list, and we hope the relevant terms are on the top. Now we have to put a number to that, which takes a bit a little time to explain. Let's just say if the relevant items are on the top, it's more 100%. If the relevant items are at the very bottom, it's 0%. The thing is called mean average precision, and the idea is that I insert to the system a lot of queries, and I see if it works for all of them, or on average, how well does it perform. So 100% mean average precision is what we want, and we performed a couple of experiments. So the first one was to be strictly in the scenario, no machine learning allowed. I have one sample, and I compare it to the rest, and that's it. And we have chosen a couple of references. So in this field, this sequential representation of handwriting is really state-of-the-art. You have an analysis window that moves over the handwriting, has some local description of the handwriting, and then the sequences are matched. And the question is, what kind of features do we use? Early on, there's some geometric features that we have tested. The histogram of oriented gradients are also mentioned during the conference. This is also a nice set of features. And we also use that autoencoding features that are learned by a CNN without taking labels into account. So that's allowed. We can analyze the data. And we compare it with the graph-based approach, and we can really quite confidently say that the approach is solid. It achieves a state-of-the-art results. You can see at the end. So for those two data sets, we were the best in the class, and we had around 70 or 80% relevant items to the top. So we believe this can be a really useful search instrument. And then, because the numbers were so good, we thought, okay, let's make it more challenging, and let's allow machine learning. So let's put in some labeled data. This word is that, this word is that, or text lines, just transcribed images. And when we do that, we are no longer the best of the class, clearly. And we had a look at this competition that was held on the Concils-Protokolle and the Botany dataset in 2016. The second row that you see there is a convolutional neural network with a nice representation of the handwriting. That's called pyramidal histogram of characters. PHOC for short, and this is called the PHOC network. And it has achieved amazing results. This was really mind-blowing at the time. And some other machine learning systems that make use of this labeled data. But when we compare our graph-based approach, we still feel confident to say that it achieves quite respectable results. We are again in the area of 70, 80%. It's a different data, it's two different data sets, similar results. And we can even see that in some of the cases, we outperform methods that have used learning. So even without the learning, it was possible to achieve something respectable. And now we have promised that we will come back to the trail. So one question that remains is, well, you have all your graph representations, you like them, and you have labeled material. How can you make use of this training set? And indeed, I think this is a good outlook. There is some recent work in deep learning that I find absolutely fascinating. For example, this work here from the Stanford University, the GraphSage network that was proposed, they try to adopt the same concept that we use for images, where we convolve information from our neighbors to the graph, because each node in the graph has also neighbors. So we can also convolve the information. The only difference is that the number of neighbors is variable. This is difficult to cope with, but there is now some methods that can use machine learning on graphs, and this is some of our current activities actually explore these possibilities. But for today, I would like to conclude, and I hope I could convince you on this little side trip that graphs are a powerful data structure for representing handwriting. We have seen during the conference quite naturally a few intermediate graph representations. Most of the time, at the end, features were extracted. But we saw the graphs. And in this work, we argue, why not use the graph directly? We have seen for keyword spotting, for this task, there's quite a strong performance using this approximative edit distance. And we know that potentially we can use machine learning as well. And the last point is also important for me to say. I believe that there is a certain advantage by the fact that we describe the graph in the handwriting in a semantically meaningful graph. It might be a quite natural bridge between what you are doing in your, I address the paleographers in the room, to put all your knowledge that you have in the taxonomy, for example, in archetype, for the different writing systems, and try to think about how would I build my graph. Maybe for Chinese handwriting, it's all about straight lines and curved lines that are somehow composed. They have a geometrical relationship between them. And the good news is all ideas are welcome, and the framework basically can handle them. And so an additional advantage might be that it's an easier way to communicate with the machine and back, so maybe it's also easier to interpret the results that have been computed on a data structure that we understand. And I dare say a matrix of pixels is really hard to understand, but a graph might be a bit more approachable, let's say. If you have questions about all of that, of course, you can ask me, or you can also have a look at our book that we wrote on the topic. With that, I conclude. Thank you.